So as I said, the only thing that I want to cover extra in this function is transcendental functions. What do I mean by transcendental functions? They are functions that I mentioned before. Ex, ln x, trig functions, and inverse trig functions. I want you to always remember, how does Ex look like? Looks like this. What does that mean? It means that the limit at minus infinity of Ex, what happens on the left tail as x goes to minus infinity? What do you notice? Ex approaches 0. Limit as x approaches plus infinity of Ex is what? When x grows to plus infinity, what's happening to the function? It's growing to plus infinity as well. So this is very important. Ln x looks like this. It doesn't have a limit at minus infinity because it's not defined there. Doesn't have. It has two limits that we need to remember. It's the limit as we approach 0 from the right, because again, limit as we approach 0 from the left does not happen. It's not there. Does not exist. The function is not defined there, so no limit talk there. The limit as x approaches 0 from the right. When we approach 0 from the right, what's happening to the function? The function is going all the way to minus infinity. The other limit that you should remember is the limit as we grow. What's happening at the tail of the function? At the tail of the function, when x grows to plus infinity, what happens to ln x? It goes all the way to plus infinity as well. Trig functions, cosine and sine, there's nothing to worry about them. Only tan and cotan. We have already discussed this. The limit of tan at pi over 2, you have to remember it. I've done it in this session, so I'm not going at. And the limit of cotan at zeros and pi's, again, I did it in this session. The only one more thing you need to remember, limits of inverse trig functions. Like sine inverse, cosine inverse, and so on. And tan inverse. How do tan inverse x look like? It looks like this, if you remember, where it lies between minus pi over 2 and pi over 2. So what is very important about tan inverse x is the tails. Not tan x, tan inverse x. Tan x does not have limits on the tails. We cannot say limit as x approaches plus minus infinity of tan x or any trig function. Why? Because trig functions are oscillating always. This means at infinity they have no limits. We cannot tell what the limit is. All right, so please remember that. But we can tell what the limit of tan inverse x at minus infinity is. As x goes to minus infinity, what does the limit of tan x look like? Minus pi over 2, because we're approaching this horizontal line. And what is the limit of tan inverse x as we go all the way to plus infinity? When you go to plus infinity, you approach what? Pi over 2. Cotan inverse has the same behavior, but between 0 and pi, and decreasing, not increasing. It looks like this. So the limit as x approaches minus infinity of cotan x is what? Pi. And the limit as x approaches plus infinity of cotan x is what? 0. Those limits, I want you to memorize them. You always have to remember them. Where is the trick? And you are never asked to answer those questions directly. What we do all the time is we do composition. So we use more than one function at a time. But already we know how to handle composition. If I want to handle this is E composed with this function. What do I do first? I do the limit of the function first. When x approaches 0 minus, what does 1 over x approach? Minus infinity. So I call 1 over x u, and I make u head to where? To minus infinity. Then at minus infinity, what's the limit of e to the u at minus infinity? The limit of e to the u as u approaches minus infinity is 0. So the final limit is 0. What's the limit here? Again, I ask myself the inside function, 1 over x. What's the limit of 1 over x at 0 plus? It's plus infinity. So I call it u and I make u go to plus infinity. What's the limit of eu as u approaches plus infinity? I go to the limit that I have memorized. At plus infinity, e to the x goes to plus infinity. So this goes to plus infinity. So this is the idea. You have to do composite functions. All right. Now, before moving to the exercises, example 5.11 and above are not included. So please do not solve them. Finding the size of animal, I don't know what, is not included. All right. Now, some problem solving, because we learned a lot this session. We learned about limits at infinity. We learned about infinite limits. We learned about asymptotes and so on. So you have to be very careful. There are some questions that you can directly solve, so I will not mention. Like here, what is the limit of x squared plus 2x minus 1 over x squared minus 4 as x approaches minus 2? I substitute minus 2. This is my first step. I get 4 minus 1. So minus 1. So x squared plus 2x minus 1 over x squared minus 4. I substitute, I get minus 1 over minus 2 squared 4 minus 4, 0. Number over 0, دغري, one shot, you do not think about it. This means we have plus or minus infinity, which means 0 is a vertical asymptote, which means that I need to check the left side and the right side, each one on its own. How do I do that? I take a hypothetical number. A number here less than 2 is minus 2.001, and the number bigger than 2 is minus 1.999. And I take those values and I substitute them in my function just to know. I know the answer. What is the answer? It's infinity. I just need to check the sign. Is it plus infinity or minus infinity? So what I do is I take bracket minus 2.001 squared plus 2 times minus 2.001 minus 1 over, see, I don't use the calculator very often. You are much better at this than me. Minus 2.001 squared minus 4. What do you get? Negative number. So this means it's negative infinity here. Do not assume this is positive. What do you have to do? You have to check it all over again. So you put minus 1.999 and you change it to minus 1.999 and minus 1.999. The answer will be positive 250. So this means it's plus infinity from this side. These are called infinite limits, not limits at infinite limits. We get limits that are infinite, infinity at the end. I leave some problems for you to try on your own. Let's look at this. Look at number 9. Those are questions you can answer directly. Limit at infinity. What do we think? When I see limit at infinity, I think leaders. Who's the leader? X squared over 3x squared. The same. This means that 1 over 3 is my limit and y equal 1 over 3 is my horizontal asymptote. Here the same. 2x squared over 4x squared. So 2 over 4 is your horizontal asymptote. Look at number 11 though. 11 is interesting because it's one of the common mistakes. 11. Limit as x approaches minus infinity of minus x over 4 plus x squared. Again, this is limit at infinity. So I want power struggle. Highest power up over highest power down. Highest power up is clear. Minus x. What's the highest power down? Directly, students, what do they say? The highest power down is x squared. No, what about the root? So it has to be root of x squared. Big important notice. Big one. Very scary notice. Many students say root x squared is what? X. That's not the case. Root x squared is absolute value of x. Let me give you an example. Root of minus 2 squared, what is it? Minus 2? Can a root be going? No. What do you have to do? It's 2. Because minus 2 squared is 4. Root 4 is 2. So the answer from root x squared should always be positive. And the students mostly do not remember. So root x squared is always absolute value of x. So that's why it's a very important question, because students mix it up all the time. They write x all the time. Root x squared, they write it as x. It's wrong. So minus x, or you tell me, what do I do with absolute value? We know how to work with absolute values. If we're at minus infinity, this means that we have negative numbers. How do negative numbers go out of the absolute value? They go out of the absolute value as minus x, because a negative number, to change it to a positive, you need to multiply it by a minus sign. See, minus x over minus x, what's the answer of the limit? 1. So y equals 1 is a horizontal asymptote. This is very important. If you forgot to put the absolute value, you'll get minus x over x, and the limit of minus x over x would be minus 1. So your full answer will be a wrong answer. So please be very careful regarding this. What if it was, so this is just an additional question. What if it was like this? Third root of 4 plus x squared. What would you do? This will be the limit. What's the highest power up? Minus x. What's the highest power down? It will be x third root of x squared, which means it is x to the power 2 over 3. Which one is the higher power? At 1 or 2 over 3? 1 is bigger. So who is in control when we simplify? 1 minus 2 over 3, 1 over 3. So the upper part is in control. When we put infinity, infinity to the power 1 over 3 is infinity, and there's a minus sign, so we get minus infinity. So these are the examples that I want you to be careful about. Also, examples that you need to know how to solve are examples like number 13. Limit as x approaches infinity of ln x squared plus 1 over x minus 3. Composite functions. To get this, we do the limit of the inside first. What's the limit of the inside at infinity? See, x squared plus 1 over x minus 3 is a polynomial rational function. So its limit at infinity is the limit of the highest power up over the highest power down. When we simplify, this gives me x. What's the limit of x at infinity? It's infinity. So all of this, if I call it u, what is u heading to when x approaches infinity? It heads also to plus infinity. Now ln u looks like this. When u goes to plus infinity, what does ln u go to? It goes to plus infinity as well. So we do it one layer at a time in order to be able to finish. Look at number 15. The limit as x approaches 0 plus of e to the minus 2 over x cubed. Again, I use the 0 plus first on the, I wrote it twice, on the composite function. What's the limit of this as x approaches 0 plus? When x approaches 0 plus, x cubed is 0 plus as well. So minus 2 over a very, very small number is minus infinity. So I change it to u and I make u go to minus infinity, because when I substitute 0 plus in minus 2 over x cubed, I get minus infinity. What's the limit of e to u to the minus infinity? This is what e looks like. So if we are going to minus infinity, e is approaching 0. So these are very good examples for you to solve in order to know. Number 18 with secant inverse, I don't want you to cover it. Number 19, limit of sine e to the power minus 1 over x squared. Composite functions, each one in a row. I start with the inside. At 0, what happens to minus 1 over x squared? It becomes minus infinity. So I call it sine EU, and I make u go to minus infinity. And then what's the next layer? What happens to EU at minus infinity? At minus infinity, EU approaches 0. So it becomes sine V if you want, where V goes to 0. What's the limit of sine V as V goes to 0? I substitute 0. Sine 0 is 0. One step at a time, not more than that. One step at a time. Look at this. Limit as x approaches infinity of sine tan inverse x. Again, I start in the inside. At infinity, what happens to tan inverse x? Tan inverse x looks like this. At infinity, here, tan inverse x approaches what? Pi over 2. So this becomes sine u as u approaches pi over 2. What's the limit of sine u at pi over 2? It's nothing but sine pi over 2, which is equal to 1. So these are very important things that you should solve. They are nice, hatta if you know how to solve them one step at a time. You do not rush into things. Tan inverse ln x, one step at a time. Ln x at 0 plus, what does it have? What happens to it? As we approach 0 from the right, ln x goes to minus infinity. So I call it u and I make it go to minus infinity. What's tan inverse u as u approaches minus infinity? Tan inverse is like this. As u approaches minus infinity, tan inverse will approach minus pi over 2. And this is our answer. Now, these are kinds of questions you're responsible for. Finding limits whose answer is infinite or whose answer is, or who are limits at infinity. Another example you're responsible for is finding vertical asymptotes and horizontal asymptotes. How do we find vertical asymptotes and horizontal asymptotes? Let's look at this. F of x equals x over 4 minus x squared. To find vertical asymptote, we need to find domain of definition, just like before. X is defined everywhere. 4 minus x squared is defined everywhere. But 4 minus x squared, because in the denominator, it cannot be 0. So x cannot be plus or minus 2. So how many discontinuities do we have? 2 discontinuities. X equals 2, x equals minus 2. I find the limit about 2. What is the limit about 2? It is 2 over 0 directly. معناتها x equals 2 is indeed a vertical asymptote. At minus 2, what's the limit? It's minus 2 over 0. Directly again, I know x equals minus 2 is a vertical asymptote. Now this is finding vertical asymptotes. How do we find horizontal asymptotes? To find horizontal asymptotes, we need to study the limit at the tail. So I need to find the limit at the tail. So I bring the same example. Y equals x over 4 minus x squared. What's the limit as x approaches plus or minus infinity of this? It's the highest power up over the highest power down. Common mistake, students forget that this minus is in our coefficient. So the highest power up is smaller than the highest power down. Directly the answer of the limit is 0. This means y equals 0 is a horizontal asymptote from both sides, because when it's 0, it doesn't matter whether it's plus or minus infinity. The only case where it matters whether it's plus or minus infinity is the case where we don't have a horizontal asymptote, because when we do have a horizontal asymptote, either it's a over b, so it's not affected by this, or it's 0, so again it's not affected by this. So over here y equals 0, so this means no oblique asymptotes directly. When we have a horizontal, we don't have an oblique. When we have an oblique, we don't have a horizontal. Whereas look at part B of the same number. When you just change a little bit of this, the vertical asymptotes will not change. They will still be plus and minus 2. But the horizontal asymptotes will change, because now what's the highest power up? X squared. What's the highest power down? minus x squared. They have the same limit, so the result will be 1 over minus 1, which is minus 1. So what's the horizontal asymptote? Y equal minus 1. What's the oblique asymptote? None. No oblique asymptotes. Look at example number 29. We want to find y equal x cubed over 4 minus x squared. Find the oblique asymptote. How do I know I have an oblique asymptote? First, I need the limit at infinity. I notice that the highest power up is x cubed, the highest power down is x squared, which means that the power up is bigger than the power down by 1. But we need to get the limit. What's the limit of this when we simplify it? It's minus x. So when x is plus infinity, the answer is minus infinity. When it is minus infinity, it is plus. Did you notice? I put them in the opposite order to show that when it was plus infinity, the limit was negative. When it was minus, the limit was positive. But now how do we find the oblique asymptote? Because the power up is 1 bigger than the power down, we need to do what? X cubed, 4 minus x squared. You actually write it as minus x squared plus 4. Always. So what do we multiply minus x squared to get x cubed? Minus x. Minus x squared is x cubed minus 4x. You subtract the result. X cubed minus x cubed cancels. Plus 4x. This has a smaller power than this. This means that we stop division. And when we stop division, the quotient we got over here is our oblique asymptote. All right. This is everything that I want to cover in this section. There's nothing other than that. So this is chapter 1 as a summary of what we've done in section 1 and what you're responsible for your quiz next week. We've done limits graphically from the graph. We have done limits algebraically. We substitute first. And when we substitute, if we get a number over 0, this means we have a vertical asymptote and the limit is plus or minus infinity. If we get 0 over 0, this is an alarm to do more work. And if we get a normal number, then khalas, we're done. No need to do anything. Now for the more work, we have learned so many ideas. We have learned how to factor. We have learned how to multiply by the conjugate. We have learned the special limit, the limit of theta approaches 0 of sine theta over theta is equal to 1. We have learned the sandwich or the squeeze theorem. We have learned how to simplify fractions and take common denominator and all of these things. So these all we have applied them in order to factor, to find limits. After talking about limits, we talked about continuity. Also, you need to talk about continuity graphically, and you have to talk about continuity analytically. We said that when we are talking about a function f of x, then continuity means finding the domain, the same. But when we talk about piecewise functions, we find the domain of parts, of pieces, but on top of that, we need to look at the separation point. To study continuity, there are some discontinuities. Discontinuities happen either in the form of a hole, which is a removable discontinuity, and you can do extensions to remove it, or in the shape of a jump, or in the shape of a vertical asymptote, which both are called non-removable. We also discussed limits, limits at infinity and infinite limits that we just talked about today. Good luck. Thank you.